Assalamu alaikum warahmatullahi wabarakatuh.
Ever look at a high-tech exercise machine and wonder how it creates exactly the right resistance, mimicking heavy weights without, a single plate? Or maybe you've seen a simple online video showing you how to build a tiny electric motor from just wire and a battery. What if these two worlds, the advanced gym and the basic physics experiment, are actually connected by the exact same fundamental ideas?
Oh, they absolutely are, yeah. The core principles that make a simple coil spin over a magnet, they're the very same ones scaled up and controlled precisely. Controlled to simulate complex loads and sophisticated exercise equipment, and even, interestingly, tap into the energy you're creating.
Right. That's the connection we're diving into today. We're taking a deep dive into electric motors, understanding how they work, exploring how you might build them yourself, and then seeing how this foundational technology shows up in some pretty surprising ways, especially in exercise and health. We'll also pull back the curtain a bit on some interesting areas where, well, our knowledge is still catching up.
Yeah, we've gathered quite a stack of material for this deep dive. It covers everything from the basic physics of motors, the principles, and hands-on building guides with safety tips, naturally. But also how motors simulate resistance in machines, this intriguing idea of generating energy from your workout. The practical realities and the economics of that energy capture, which are quite sobering, and crucially, some identified blind spots in the related exercise research.
Okay, so our mission is to take the most important nuggets from these sources, connect the dots between the science of motors and the mechanics of human movement, and give you a real shortcut to being well-informed on this fascinating intersection. Okay, let's unpack this, starting with the absolute core idea behind electric motors.
Right. At its most fundamental level, an electric motor is simply a device that converts electrical energy into mechanical energy, typically, rotational motion, something spinning.
And this conversion happens thanks to a core physics principle. There's a specific law.
Exactly. It's governed by Lorenz's force law. This law basically describes how a wire carrying an electric current experiences a force when it's placed within a magnetic field. What's key, though, is that the force is always perpendicular at right angles to both the direction the current is flowing and the direction of the magnetic field lines.
So current goes one way, magnetic field another, and the force pushes kind of sideways to both of those.
That's a great way to visualize it, yeah. And in a motor, components are arranged very specifically. So this force creates torque, that rotational push that makes something spin.
Got it. Torque. And all motors need a few key parts to make that happen, right? You can't just have a wire and a magnet floating around.
They do. Generally, every motor has a stationary part, the stator, and a rotating part, the rotor, or sometimes called the armature. The stator creates the magnetic field. It might use permanent magnets or sometimes electromagnets, coils of wire that become magnetic when current flows through them.
Okay, so the stator is like the static magnetic stage, the fixed part.
Right. And the rotor is the dynamic player. It usually holds coils of wire or sometimes magnets itself that interact with the stator's field, and, well, that's the bit that spins.
Okay, so current in the rotor wires interacts with the stator's magnetic field. Lorentz force kicks in, creates torque, and the rotor spins. Makes sense. But hang on, if the current is just flowing in one direction, wouldn't the rotor just kind of line up with the magnetic field and then stop?
Ah, that's the critical challenge. You've hit on it. For continuous spinning, you absolutely need a system to constantly flip the direction of the current in the rotor windings, and it has to flip at just the right moment as it turns. In simpler, like DC motors, this is often handled by a physical commutator and brushes, little contacts. In more advanced designs, it's all done electronically by a controller. But either way, this switching ensures the force keeps pushing the rotor around and around.
Okay, so the commutator, the controller, is basically redirecting the current constantly to keep the rotation going, to keep that push happening.
Precisely. It's maintaining that consistent torque. And here's where it gets really interesting and ties into exercise later. The same fundamental principle of electromagnetic induction that powers a motor also means you can use an electric motor as a generator.
Wait, the exact same device can do both things, motor and generator.
Yes, exactly. Feed it electricity, you get motion out, that's a motor. But apply mechanical force to make it spin like you physically turn the shaft, that movement within the magnetic field induces an electric current in the windings. That's a generator. This dual capability is a truly important nugget from the sources, and it's absolutely essential for what we'll discuss later with exercise machines.
That is a fantastic nugget.
Yeah.
Okay, knowing that principle, let's talk about building one. It might sound complex, maybe intimidating, but you can actually build a simple motor at home, right?
You absolutely can. It's a classic science project, really, and a brilliant way to see these principles in action. You can build a basic electric motor with surprisingly simple stuff, things you can easily get.
What kind of stuff are we talking? Like high-tech parts, lab equipment?
Yeah. Not at all. Not for a simple one. Think insulated copper wire, usually called magnet wire. Some strong permanent magnets, neodymium ones, work really well. They're quite powerful. A standard battery, like an AA or a D cell. A couple of paper clips, believe it or not. Some sandpaper, wire cutters, maybe pliers. Basic things.
Okay, yeah, things you might find in a drawer or pick up easily. And one of the most common projects uses just a simple loop of wire, is that right?
That's the classic demonstration motor. You wind the copper wire into a coil that's your armature. You create an axle using the ends of the wire. And here's the really crucial step, something highlighted in the sources. You only sand off the insulation from one side of those wire ends, just one flat side.
One side only. Why is that specific detail? Sanding just one side. Why is that so important?
Yeah. That asymmetrical sanding, it's the key trick. It's what makes this simple design spin continuously. As the coil rotates, the exposed sanded side of the wire touches the supports like bent paper clips connected to the battery. That completes the circuit, current flows, you get the magnetic push. But then, as it keeps turning, that bare side rotates away and the insulated side touches the support. That momentarily breaks the circuit. No current, no push. But inertia carries it around until the sanded side makes contact again. This timed on-off current flow, driven just by the rotation itself, provides the necessary kicks to keep it turning, rather than just swinging once and stopping. It creates its own very basic form of commutation.
That's really clever, using the insulation itself for the timing.
Yeah.
Genius. I've also seen a different simple design, one that spins using just a battery, a screw, and a magnet.
Yes, that's another popular one, often called a homopolar motor. It's very simple. You usually stick a neodymium magnet onto the head of a steel screw. Then you stand the screw point down on the positive terminal of a battery. Then you just touch a piece of wire from the negative terminal to the side of the magnet.
And that spins too, just like that.
It does. The current flows from the battery terminal, up the screw, through the magnet to where the wire touches it, and then through the wire back to the other battery terminal. This current flowing radially through the magnet, within the magnet's own field, experiences that Lorentz force, causing the magnet and screw assembly to spin. It's another really neat, stripped-down way to see the force at work.
So simple projects are definitely accessible, fun ways to see the physics. But okay, even with simple projects, safety is always the priority, right? Especially with electricity and magnets.
Absolutely critical, yes. Even these low-voltage battery projects involve basic electrical principles, sharp tools, things that need careful handling. First off, always use low-voltage batteries like AA or D cells. That avoids any real shock risk. And get in the habit of disconnecting the power. Just take the battery out before you adjust anything.
Yeah.
Fiddling with wires while it's live is asking for trouble.
Always a good rule, yeah. Don't fiddle live.
Then use sharp tools carefully, wire cutters, pliers. Always cut wire away from yourself. And with strong magnets, particularly neodymium, be really cautious. They can snap together with surprising force and give you a nasty pinch. Ouch. They can also damage electronics phones, credit cards, or, very importantly, affect medical devices like pacemakers. Keep them well away from those.
Good points. And safety glasses seem like a no-brainer too.
Definitely. Always wear safety glasses, protect your eyes against flying wire snippets or maybe a tool slipping, and just, basic stuff. Keep your workspace clean, well lit. It always helps prevent accidents.
Okay, so you can start with these simple demos, see the principles, but obviously electric motors in the real world get way, way more complex than a wire loop in a battery.
Oh, significantly more complex, yeah. Moving beyond these sort of educational setups, motors become precisely engineered systems designed for demanding applications. Think about brushless DC motors, often called BLDCs.
Right, BLDCs. Those sound like they're in a different league altogether.
They really are. These are common in things like drones, robotics, high-performance appliances, electric vehicles, lots of modern tech. They completely eliminate the physical brushes and the commutator that wear out. Instead, electronic controllers precisely switch the current to stationary windings in the stator in a very specific sequence. This creates a magnetic field that effectively rotates electronically. Permanent magnets mounted on the rotor then just follow this rotating field.
Ah, so no physical contact for the switching part. That must improve things quite a bit.
It certainly does. You generally get higher efficiency because there's less friction, better reliability because there are fewer parts rubbing and wearing down, and often a higher power density, meaning more power output for a given size and weight.
And professional manufacturing, Producing these things on a large scale must be a whole different world of complexity.
Completely, yes. Producing motors for, say, industrial machinery or electric cars involves incredible precision engineering, integrating sophisticated control systems and software, using advanced materials for magnets and windings, and often applying protective coatings. The sources mention things like primers to prevent rust and help paint stick properly. And then there's rigorous testing, absolutely paramount. Simulating fault conditions, endurance testing, making sure they're reliable and safe, especially in critical applications.
Okay. All right, we've explored the fundamental physics, how to build simple motors, seen how complex they can become. Now, let's bring it back to the gym where we started. How does a piece of technology like an electric motor actually connect to simulating weights? That still feels like a bit of a leap.
Well, this is where that aha moment really lands. Because electric motors can be controlled to precisely simulate the feeling of lifting a physical weight.
Simulate. But how? There aren't actual weight plates hidden inside these machines, are there?
No, exactly. Instead of just letting the motor spin freely, like in a fan, the motor connected to the exercise equipment is actively controlled, usually by a pretty sophisticated computer system. It's controlled to produce what's called a resistive torque. You can think of resistive torque as the motor actively pushing back against your movement with a controlled twisting force. By precisely adjusting the amount of electric current flowing into the motor windings, the system can control exactly how much opposition, how much resistance you feel.
So it's actively resisting you, fighting back in a controlled way.
Right. It's essentially mimicking the sensation of gravity pulling down on a physical weight, or maybe the inertia you feel when you try to accelerate a heavy mass. Sensors on the machine constantly monitor your position and speed, sometimes even the force you're applying, in real time. This feedback goes to the control system, which then dynamically adjusts the motor's current and therefore its resistance to maintain whatever load profile has been programmed.
And it can simulate different types of resistance, not just like a constant dumbbell feeling.
That's one of the major advantages, yeah. These systems can simulate really complex resistance profiles. They can give you constant force, just like a free weight, sure. But they can also simulate variable inertia, where the resistance feels different depending on how fast you try to move. They can even simulate complex strength curves, so the resistance changes throughout the range of motion of an exercise, maybe making it harder where you're naturally stronger and easier where you have less leverage, tailored to you and the exercise. And importantly, they can simulate any muscle contraction mode concentric, which is the lifting phase, eccentric, the lowering phase, or even isometric, just holding still against the force, all by controlling the relationship between force and velocity.
Wow. Okay, can you walk through an example, like say simulating a specific weight for a common exercise, maybe a squat?
Sure. Let's take simulating a 100-kilogram squat. That's about 220 pounds. The motor, working through whatever mechanical connection it has to you, cables, pulleys, a direct linkage. It must be controlled by the computer to generate a resistive force equivalent to the gravitational force on 100 kilograms. That's a roughly 980 newtons of force. And the key is, it has to generate that 980 newton resistance throughout the entire up and down motion of the squat. The sensors are constantly feeding back your position and speed, allowing the system to adjust the motor current microsecond by microsecond to ensure that 980 newton resistance feels consistent, whether you're near the bottom or near the top of the movement.
That's incredible precision compared to just, gravity acting on a stack of iron plates.
Mhm.
Are these systems actually out there in gyms or rehab centers?
Oh, yes, they are. This kind of technology is definitely used in highly advanced fitness and rehabilitation equipment. You might see it in things like linear motor-driven leg presses, some sophisticated robotic treadmills that can provide bodyweight support but also control resistance precisely, and some high-end commercial strength machines that are specifically designed to replicate the feel of free weights, but with all the benefits of digital control, programmability, and data tracking.
Okay, so simulating weights is one really cool side of this motor connection. But you also mentioned earlier, quite intriguingly, that motors can be generators. Does that principle apply here too in exercise?
It absolutely does. And this is the other really fascinating nugget the sources highlight regarding motors and exercise. Since electric motors can function as generators, exercise machines equipped with them have the potential emphasis on potential to actually create electricity while you're working out.
So wait, while I'm like pushing or pulling or pedaling, getting my sweat on, I could also be generating usable power.
That's the core idea behind what's called regenerative operation in this context. When you, the user, are the one driving the mechanical movement. For instance, when you're lowering a weight under control during the eccentric phase of a lift, or maybe pedaling on an exercise bike, or the belt is moving under your feet on certain treadmills. The motor essentially reverses its function. Instead of consuming electricity to create motion, your motion makes it spin and it acts as a generator, converting the mechanical energy you're putting in back into electrical energy.
Okay, that sounds a lot like regenerative braking in an electric car, right?
Precisely the same principle, yeah. In an EV, when you brake or lift off the accelerator, the motor turns into a generator, capturing kinetic energy that would otherwise be wasted as heat in traditional brakes and sends it back to the battery. In certain types of exercise equipment, the energy you expend doing the work can be similarly converted back into electricity, instead of just being dissipated as heat in some internal resistance mechanism.
Okay, so where does that generated electricity actually go? Does it just vanish?
No, it can be used in a few ways depending on the machine's design. In simpler setups, it might just be enough to power the machine's own display and electronics, reducing its net power consumption. In others, it might be stored temporarily in an integrated battery pack within the machine. Or, in more ambitious setups, it can be converted and actually fed back into the building's electrical grid, the gyms, or maybe even your homes.
Whoa, sending it back to the grid from my exercise bike. That sounds pretty complex. How would you even make that happen at home? Is that realistic?
It's definitely not plug and play. It's quite an undertaking. First, you need the right mechanical coupling, obviously, from your movement, the pedals, the belt, whatever, to the generator component itself. Then you need a fair bit of electrical conversion hardware. Typically, a rectifier to change the generated power, which might be variable AC or DC, into stable DC. And then, crucially, a sophisticated inverter to turn that DC into AC power that perfectly matches the voltage and frequency of your home's electricity grid. Synchronization is key. You might also want a battery bank to store the energy if you're not using it immediately. And you absolutely need a grid tie inverter, which is specifically designed for safely synchronizing and feeding power back to the grid. Plus, proper safety measures like circuit breakers and isolation switches are vital. And critically, you'd almost certainly need formal approval from your local utility company, likely involving a net metering agreement, to legally and safely send power back.
Okay, yeah, that sounds like a significant engineering project, not just buying a fancy bike. But there are places actually doing this commercially, in gyms.
Yes, there are examples out there. A few companies, the sources mention names like Rerev and Sports Art, produce lines of gym equipment ellipticals, bikes specifically designed with this regenerative capability. They're engineered to generate utility-grade electricity that can be fed back into the building's power supply. And there are some gym facilities, sometimes branded as green microgyms or similar concepts, that have been built specifically around leveraging this idea, aiming to generate a portion of their own power from members' workouts.
This all sounds incredible. I mean, if electric motors can simulate any weight precisely, and our exercise can actually generate electricity, it leads to the obvious question, why aren't gyms paying people to come work out? Or why isn't my high-tech home exercise bike powering my entire house? There must be a catch.
Ah, yes. This brings us to a really important practical point, a key nugget from the sources that deals with the limits of this exercise power generation. The big, fundamental question is, how much energy can a human realistically produce through exercise?
Enough to make a difference, surely, if you work hard.
Well, unfortunately, the amount of power a human can sustainably generate is actually quite small, surprisingly small for most people. While an elite athlete might hit several hundred watts, maybe even over 1,000, for very short bursts, and a fit person might sustain 5,100 watts during intense intervals. Typical steady output during a moderate workout is much, much lower. We're talking maybe only a few watts from just casual movement, or perhaps around 20 to 30 watts from sustained, moderate intensity effort, like steady cycling.
20 or 30 watts, wow. That's barely enough power for a small LED light bulb, maybe a laptop charger on low power.
Exactly. It puts it in perspective. And remember, that's just the raw mechanical power you produce. When you try to convert that mechanical energy into usable electricity, you lose a significant portion through inefficiencies, friction in the machine's mechanics, losses within the generator itself as it converts motion to electricity, and losses in the power electronics needed to condition and invert that electricity. So the actual usable electrical power you get out is even less than that modest starting point.
So the economic reality isn't quite as, well, green or promising as the concept might initially sound.
Not for powering a home or creating a business model around paying people to exercise, no. The sources are pretty clear on this. The cost of the specialized, efficient equipment needed to capture this small amount of energy effectively plus the installation costs, ongoing maintenance, and the complexity of managing that energy. Storage, grid tie inverters, regulations. It just far, far outweighs the actual monetary value of the tiny bit of electricity generated. One source calculated that a 5-kilometer run, even if you could somehow capture all the energy perfectly efficiently, might only generate about 36 watt hours of energy.
Okay, 36 watt hours. How much is that worth in like dollars and cents?
Well, if your electricity costs, say, 15 cents per kilowatt hour, which is 1,000 watt hours, then 36 watt hours is just 0.036 kilowatt hours. That translates to a potential saving of less than 1 cent, maybe half a cent, depending on your rates.
Less than a single cent for all the energy generated during a 5K run.
Wow, okay. That really, really puts practical economics into sharp perspective. It really does. There's simply no viable commercial business model currently to pay gym goers for their workout-generated electricity because the energy value is just far too low to cover the significant capital and operational costs of the required infrastructure. Most serious research in energy harvesting from human motion is focused on scavenging microwatts or maybe milliwatts, tiny amounts of power, sufficient perhaps for small, self-powered sensors or wearable electronics, not grid-scale power generation.
That makes perfect sense now. It's a scientifically cool idea, the physics works, but the numbers just don't scale up to power a building or make economic sense on a large scale. Okay, this leads us nicely into another really interesting area the sources touched upon, which is where this sophisticated technology meets the current unknowns in exercise science itself. If we've got this amazing tech that can simulate weights perfectly, track everything, maybe even generate a tiny bit of power, what are the big questions exercise researchers are still trying to answer about making exercise work best?
That's a critical point and a good transition, because despite all the technological sophistication we can bring to bear, there are still significant blind spots areas needing much more research in the fields of exercise science and applied biomechanics.
Like, what kind of gaps are we talking about? Are exercise programs just not working as consistently as we think?
Well, sometimes we see exactly that inconsistent effectiveness when applying exercise interventions, even carefully designed ones, to specific groups or conditions. For instance, some sources highlighted studies looking at exercise programs designed to help fighter pilots who experience neck pain from pulling high G maneuvers. The results were mixed. Some studies reported pain reduction, others found little benefit. This kind of inconsistency suggests we don't fully understand the optimal protocols, the best exercises, the right intensity, frequency, duration, or perhaps how individual differences between pilots might influence who responds and who doesn't.
Hmm. So the tech might be precise, capable of delivering any protocol, but knowing the best protocol to deliver for whom, under what conditions. That's still an open question sometimes.
Exactly. Another blind spot pointed out was the quality of reporting within exercise research itself. Reviews looking at studies on exercise for common conditions, like shoulder impingement syndrome, often find that the papers do a poor job of describing the precise details of the exercise protocols that were actually used. Things like exact resistance levels, progression rules, specific techniques. They're often vaguely described. This makes it incredibly difficult for other researchers to replicate the study accurately, or for clinicians, physical therapists, to translate those findings effectively into their daily practice.
Yeah, if you can't clearly understand and reproduce what was done in a study, it's really hard to build confidence in its findings or apply them reliably.
Right. And then there are simply areas that are understudied. Take early interventions post-surgery. For example, proprioceptive training, that's exercises focusing on balance, joint position sense, body awareness. It shows promise for improving function after total knee replacement surgery. But the sources suggest more research is needed to really nail down the optimal timing. How soon after surgery should it start? What intensity? What specific types of exercises are most effective? The details aren't fully worked out.
Makes sense. What about the challenge of just getting people to do the exercise and stick with it long term? Is that a blind spot too?
Oh, that's a huge area with significant blind spots.
Yeah.
Understanding and overcoming behavioral barriers. Research looking into managing chronic diseases like hypertension reveals clear gaps in our understanding of patient knowledge about exercise, their beliefs, their motivation, and ultimately their adherence to prescribed exercise programs. These factors are often influenced by demographics, socioeconomic status, cultural factors, and behavior patterns. We really need more research into developing tailored interventions that specifically address these individual barriers, particularly in diverse populations, and maybe in settings where resources are limited. One size definitely doesn't fit all.
And applying this to specific demanding jobs, like first responders.
Yes, exactly. Occupational injury prevention is another area. The sources specifically pointed out a lack of targeted, evidence-based exercise programs designed for high-risk professions like firefighting. Firefighters face unique physical demands and injury risks, and generic fitness programs might not be sufficient. We need programs truly grounded in the specific tasks and risks of their job.
So lots of areas needing more clarity in traditional exercise research. But what about the impact of the very technology we've been discussing? The smart machines, the connected fitness platforms, the apps.
Now this is a crucial blind spot identified in the sources that directly relates back to how we're applying all this advanced motor and sensor technology in exercise today. While connected fitness equipment, Pelotons, tonals, hydros, all the apps and wearables are incredibly popular and rapidly evolving, there is, somewhat surprisingly, very limited long-term data available on their actual effectiveness. We lack robust data on user adherence over extended periods, say multiple years, and critically on the measurable health outcomes, changes in fitness, disease markers, quality of life, resulting from using these platforms over those long durations.
That is surprising, actually, given how much buzz there is around them and how widely they're being adopted.
It is. We have this incredible technology that can precisely control resistance, track every possible metric, connect users socially, provide interactive content. It's amazing tech. But we don't yet have solid, peer-reviewed, longitudinal data really demonstrating how effectively using this tech translates into sustained improvements in long-term health and consistent exercise habits over many years for the average user. This was flagged as a significant gap needing much more focus.
And addressing all these varied gaps, from pilot neck pain to long-term tech adherence, it sounds like it requires bringing different fields of expertise together, doesn't it?
Absolutely. The consensus from the sources is that it really calls for truly multidisciplinary approaches. You need to combine rigorous clinical trials with insights from behavioral science to understand motivation and adherence, biomechanics to analyze movement quality and optimize exercise technique, data science to handle the large data sets from connected devices, and public health perspectives to ensure interventions reach and benefit diverse populations effectively.
Okay, let's try and bring all these threads together for you, the listener. We started this deep dive by getting into the fundamental physics of how electric motors work, how they turn electricity into motion, governed by that key principle, Lorenz's force law, and crucially, how that same principle allows them to work in reverse as generators. That was a really important nugget. We also saw that you can build simple versions at home, which is pretty cool just to see this in action.
Then we jump to the high-tech end. We explored how advanced, precisely controlled motors are used in modern exercise machines to simulate weights. They offer incredible potential for programmable, personalized resistance, mimicking free weights, or creating novel resistance profiles. And we touched on how they can even capture some of your expended energy back through regenerative operation.
Right. But then we hit a crucial economic reality check. The amount of electricity a human can actually generate through exercise is very, very small. And the cost and complexity of capturing and using that tiny amount of power far outweighs its monetary value. So powering your home or getting paid to cycle, that's pretty much off the table from a practical standpoint.
Yeah, the physics allows it, but the economics don't support it at scale. And finally, we looked at the broader context, uncovering some significant blind spots in current exercise and applied biomechanics research. Despite having amazing technology like these motor systems, we still face challenges. Inconsistent results in some interventions, poor reporting in studies, under-researched areas, behavioral barriers to adherence, and, very relevant to our discussion, a real lack of long-term data on the actual health impact and sustained usage of these newer tech-driven fitness tools over periods of years.
So understanding the motor technology inside that fancy machine gives you valuable insight into how it's providing resistance and its potential for energy capture. That's useful knowledge. But being aware of these research gaps serves as an important reminder. Just having the sophisticated tech is only part of the equation. It's a powerful tool, yes, but we're still very much in the process of figuring out how to wield it most effectively for sustained health, for optimal performance across different people and different goals. So here's maybe a final thought to leave you with. Something to ponder as you consider your next workout, whether it's lifting old school iron or logging onto a smart connected machine. If electric motors offer this incredible ability to simulate almost any resistance profile and even generate a bit of energy, and yet we simultaneously face inconsistent results in exercise outcomes for specific groups and a significant lack of long-term data on the real impact of tech-driven fitness. Does this mean we've essentially mastered the physics, the engineering side of it? Or does it perhaps highlight that we're still only just scratching the surface of understanding how to truly optimize human performance, human health, and long-term behavior using all this powerful technology. Something to think about.